Hi students, this is the last video on combinatorics. In the previous two videos, we have seen pigeonhole principle and some basic principles of counting, permutations and combinations. In this video, we are going to see an advanced counting technique called principle of inclusion and exclusion. And also we are going to see binomial theorem, extended binomial theorem and multinomial theorem, which is a generalization of binomial theorem. Inclusion and exclusion. Let's see an example here. How many numbers between 1 to 100 that are divisible by 3 or 4? Okay. Let A be the set of all numbers between 1 to 100 that are divisible by 3. Then the number of elements in A going to be the floor of 100 by 3. 100 by 3 value 33.33. If you take the floor, you will get 33. Let B be the set of all numbers between 1 to 100 that are divisible by 4. The number of elements in B going to be the floor of 100 by 4, which is going to be 25. Then we are interested in number of elements in A union B. A union B is a set consisting of elements in A or elements in B. So now question is, can we write number of elements in A union B equal to number of elements in A plus number of elements in B? That means, can we apply sum rule? Answer is no. If you want to apply some rule, you need to make sure that there is no overlapping between A and B. But A and B do overlap here. Okay, because there are numbers which are divisible by 3 as well as 4, which are precisely the numbers divisible by 12. That means what? Okay, now I think you can fix it, because we know that the numbers divisible by 12, they are counted here as well as here. That means they got counted twice. Okay. Now how to fix that? Now let's subtract once. Okay. Now let's subtract the count of the numbers divisible by 12. Then we get the correct answer. So the fix is this. Number of elements in A union B going to be number of elements in A plus number of elements in B minus number of elements in A intersection B. Okay. So now the number of elements in A union B going to be 33, which is number of elements in A, plus 25, which is number of elements in B, minus 8, which is number of elements in A intersection B, because number of elements in A intersection B going to be floor of 100 by 12. Okay, so which is going to be 8. Therefore, answer is going to be 50. There are 50 numbers between 1 to 100 that are divisible by 3 or 4. For any two finite sets A comma B, the number of elements in A union B is going to be number of elements in A plus number of elements in B minus number of elements in A intersection B. The reason is this. Let us say this is set A, this is set B, they overlap something like this. Here, when we include, here if we simply write number of elements in A plus number of elements in B according to some rule, it would be wrong. See here, when we include number of elements in A, this intersection part included once. Again, when we include number of elements in B, this got included again. That means this intersection part included twice. So that's why we exclude once. This is an idea. Including and excluding in controlled way, so that we get correct count. Okay. So that's why we call inclusion exclusion principle. Next, similarly, for any three finite set A, B, C, the number of elements in A union, B union, C going to be this. Again, here let us say this is A, this is B, this is C. Okay. Here again, according to some rule, if you simply write like this, it would be wrong. The reason is this. When we include number of elements in A, this part included once. When you include number of elements in B, this part included again. This got included twice. So we need to exclude once. We did that. Again, so this intersection part included once in B, also once in C. They got included twice, so we exclude once. Similarly, with this A intersection C part, this got included once in A, once in C. They got included twice, so we need to exclude once. But the problem is with this intersection A intersection B intersection C, they got included once in A, once in B, once in C. Also, they got excluded once in A intersection B, once in B intersection C, once in A intersection C. That means we included thrice, excluded thrice. That means they are not included at all. So we need to include one, so that's why plus A intersection B intersection C. So this is a inclusion exclusion principle for three sets, including and excluding in controlled way, so that we will not have any overcount, we actually get a correct count. Okay. Okay, generalization for n sets. Theorem, let A1, A2, so on A and B finite sets, then the number of elements in A1 union, A2 union, so on An equal to this. To the right hand side, we include count of all AIs, then we exclude count of all double intersections, then again we include all count of triple intersection, then again we exclude and so on. Okay, including and excluding in controlled way. Anyway, this can be proved using mathematical induction using the base case n equal to 2. Okay, so I will let you try this. A useful fact, let S be a universal set and A's are subsets of S for I equal 1 to n. Then the number of elements in A1 complement intersection, A2 complement intersection, so on, An complement going to be number of elements in S minus number of elements in A1 union, A2 union, so on, An. Because by De Morgan laws, I can write A1 complement intersection, A2 complement intersection, so on, An complement. We can write A1 union, A2 union, so on, An whole complement because of De Morgan laws. So therefore, by complementation principle, the count of this one going to be number of elements in universal set S minus number of elements in A1 union, A2 union, so on, An. Okay. We are going to use this fact in upcoming problems. Please keep in mind. Okay. See, this principle of inclusion and exclusion is a very powerful tool to tackle some hard sounding problems. The problems that are not straight application of product rule or sum rule. Okay. Here is a one such a problem. Problem. Say there is a class with 30 students and teacher conducts an exam of multiple choice questions to 30 students. Since test is of MCQs, he thought that it hardly make any difference whether I grade it or students themselves grade their response sheets as long as no one grading their own response sheet. So once exam done, Teacher collects response sheets and distributes back so that no one receives their own response sheet. Question of interest is how many ways can teacher distribute so that no student receiving their own response sheet? Okay, if you try a bit, you will start realizing that this problem is pretty hard unless you think in terms of inclusion and exclusion principle. Okay, let's formalize this problem. Okay, derangements. Okay, a derangement of n ordered objects. Ordered objects means objects which have some ranks like 1, 2, 3, so on n. Okay. A derangement of n ordered object is a permutation of those n objects that leaves no objects in its original position. Okay. After arrangement, no one should take their original position. Derangement is a special type of permutation with a property that nothing should be fixed. Everything should move to somewhere. Okay. No object should be in original position. Okay. Such a permutations are called derangements. Now, for n objects, we know there are n factorial permutations. Now, question of interest is how many of them actually derangements, right? So, let me introduce notation here. D sub n denote the number of derangements of n objects. Okay. Actually, in the previous problem, we were interested in D30 because the distributing response sheet in a way so that no one receiving their own response sheet is nothing but a derangement of 30 objects. Okay. So, in previous problem, we were interested in D30. Now let's try to see the general formula for Dn so that we can easily compute D30. Okay. Theorem. Dn. Dn going to be n factorial times 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus and so on minus 1 to the power of n into 1 by n factorial. Okay. So this is a count for number of derangements of n objects. Okay. Let's try to prove this. First, let us say A1, A2, so on, A and B ordered objects. Okay. A1 is the first object, A2 is the second object, so on, A and B the nth object. Okay. Let S be the set of all permutations of n objects. Number of elements in S going to be n factorial. We know. Number of permutations of n objects equal to n factorial. This is going to be our universal set here. Okay. Now let me take AI be the set of all permutations of this n objects in which ith objects in its original position. Okay. In AI, we have all permutations in which ith object is fixed in its position. In ith place, we are fixing AI. Okay. Such a permutations are collected in AI. Okay. So then number of elements in AI going to be n minus 1 factorial because in the among n positions, ith position is fixed. Now remaining n minus 1 position can be arranged in n minus 1 factorial ways. That's why. Okay. For a 1 less than or equal to I less than or equal to n. Number of elements in AI intersection AJ going to be n minus 2 factorial because A intersection AJ going to consisting of all permutations in which ith object is fixed, jth object is fixed. That means in ith position we are fixing AI, in jth position we are fixing AJ. Remaining n minus 2 positions are free, so they can be arranged in n minus 2 factorial ways. Okay. Similarly, number of elements in AI intersection AJ intersection AK going to be n minus 3 factorial. Okay. because this set is going to consisting of all permutations in which ith object is fixed, jth object is fixed, kth object is fixed. Okay, so then remaining n minus 3 positions are free. They can be arranged in n minus 3 factorial for any 1 less than or equal to I less than j less than k. Okay, next, in general, the number of elements in AI1 intersection AI2 intersection so on AI are going to be n minus r factorial with a similar reasoning. And in the same way, the number of elements in A1 intersection, A2 intersection, so on An, which means permutations in which first object is fixed, second object is fixed, so on nth object is fixed. That means it's like 1, 2, so on En. Here, first object is fixed, second object is fixed, so on, nth object is fixed. Everything is fixed, so there is only one such a permutation. Answer should be 1. That's why we are writing n minus n factorial, which is a 0 factorial, whose value anyway 1. It makes sense. Now, we are interested in this set because this is precisely consisting of derangements. See, the permutations in A1 complement intersection, A2 complement intersection, A3 complement intersection, so on, intersection An complement means what? Those permutations having these properties. These permutation in A1 complement means, see, permutation in A1 means first object is fixed. Permutation not in A1 means first object is not fixed. That's why a permutation in A1 complement means first object is not fixed. Which is also in A2 complement means second object also not fixed. Which is also in A3 complement means third object also not fixed. So on. Also in An complement means nth object also not fixed. That means none of the object is fixed in its original position. Okay, so this set precisely consisting of derangements. Okay, now we are interested in count of this particular set. Okay, so Dn going to be what? Number of elements in A1 complement intersection, A2 complement intersection, so on, An complement. Okay, now, so I mentioned a useful fact earlier. The number of elements in A1 complement intersection, A2 complement intersection, so on, An complement going to be number of elements in S minus number of elements in A1 union, A2 union, so on, An. Okay. Using principle of inclusion exclusion, this can be replaced with following expression. Okay. So we have this for number of elements in A1 union, A2 union, so on, An from principle of inclusion and exclusion. Okay, and we also know that number of elements in S equal to n factorial and number of elements in AI equal to n minus 1 factorial, and here this is going to be n minus 2 factorial and so on. Okay, next step, let's replace with these values and also let us multiply this minus inside. Okay, so Dn equal to n factorial minus summation 1 less than or equal to I less than or equal to n minus 1 factorial. So here this summation varying over I from 1 to n. So there are n terms in the summation. I would rather say n choose 1 terms, each equal to n minus 1 factorial. So this sum add up to n choose 1 into n minus 1 factorial. Okay. Similarly, this summation varying over ij where 1 less than or equal to I less than j less than or equal to n. So there will be n choose 2 terms in the summation, each equal to n minus 2 factorial. So this sum add up to n choose 2 times n minus 2 factorial. Similarly, here this sum add up to n choose 3 into n minus 3 factorial and so on. This sum add up to n choose r into n minus r factorial, and here there is only one term. We can write n choose n, okay, n minus n factorial. Okay. In next step, we will write exactly this. Okay. So n factorial minus n choose 1 times n minus 1 factorial plus n choose 2 times n minus 2 factorial minus n choose 3 times n minus 3 factorial and so on. Okay. Now, if you write n choose r formula in each term, so n choose 1 going to be n factorial by 1 factorial times n minus 1 factorial. This one cancel. N choose 2 we are writing here. This one cancel. This one cancel. This one cancel. This one cancel. So then if you take n factorial common in each term, in every term we got n factorial, right? See, we can take this one common, then you will end up with this. Dn equal to n factorial minus 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on, plus minus 1 to the power of n into 1 by n factorial. This is the formula for Dn, number of derangement of n objects. Okay. Okay, now let's get back to the problem. The number of ways teacher can distribute these 30 response sheets so that no student receiving their own response sheet equal to D30. Okay. So answer is D30. So to get the D30 value, I just write a small Python code to implement that formula, okay, that we got using one for loop. Okay. So this is the program. Let me run it to get the D30 value. Okay. Default we got a D10 value. Let me change it to 30. Yeah. This is a D30 value. This many ways teacher can distribute these 30 response sheets so that no student receiving their own response sheet. Okay. Okay, next. In the first video, we managed to count functions, one functions and bijections, but we couldn't give a count for onto functions. Okay, we were not ready. Now we are in a position to give a count for onto function from set with m elements to set with n elements. Okay, here is the theorem. Let m and n be positive integers with m greater than or equal to n. Then the number of onto functions from set with the m elements to set with the n elements equal to n to the power of m minus n choose 1 times n minus 1 to the power of m plus n choose 2 times n minus 2 to the power of m, so on. The last term minus 1 to the power of n minus 1 into n choose n minus 1 times 1 to the power of n. Okay. Here, so if m less than n, then answer is 0 because we cannot produce any onto function from set with m elements to set with n elements when m less than n. Okay, so we need number of elements in domain should be greater than or equal to number of elements in codomain to be able to produce onto function. Okay, fine. Now it's going to be exercise, but I'll get you started with a hint. Okay, let us say A be the set with m elements, B be the set with n elements. Let me list them like a B1, B2, so on, Bn. Let us say these are n elements of B. Okay, now we want to count onto functions, right? First of all, let's take s equal to all functions from A to B. Okay, like universal set. Then number of elements in S going to be n to the power of n, but because we know how to count functions, right? Now let's take ai equal to all functions from a to b such that bi is missing from range of f. Okay, I equal to 1 to so on n. For example, A1 is the set consisting of all functions from A to B in which B1 is not in the range of F. That means nothing in the domain go to B1. Okay, for those functions sitting in A1. Okay, there are some functions nothing in the domain go to B2. Those functions will be sitting in A2. Like that, AI be the all function from A to B, nothing in the domain will go to BI. Okay, that means BI is not in the range of F. Such a function will be sitting in AI for I equal to 1 to n. Okay, but onto function means nothing should be missing in the codomain. Okay, everything in the codomain should be mapped by something in the domain. Okay, such a functions are called onto functions. Now if I look at a1 complement intersection, a2 complement intersection, so on, an complement, my claim is that this set precisely consisting of onto functions from a to b. Okay, these are all onto functions from a to b. Reason is this. For example, a function belongs to a1 means what? b1 is not in the range of f, right? Function belongs to a1 complement means opposite. b1 belongs to range of f. In general, a function belongs to ai means bi does not belongs to range of f. And function belongs to ai complement means bi belongs to range of f. Okay, if any function sitting here means what, belongs to a1 complement intersection a2 complement intersection a3 complement intersection so on intersection an complement, that means f belongs to a1 complement means b1 belongs to range of f, and f also belongs to a2 complement means b2 also belongs to range of f, and f also belongs to a3 complement means b3 also belongs to range of f, and so on. F also in an complement means bn also belongs to range of f, that means b1 b2 everything belongs to range of f. That implies everything in the codomain sitting in the range, that means range equal to codomain, that implies f is onto. Okay, so that's why this set precisely consisting of onto functions. So we want count for this set. Now just proceed just like a derangement solution. Okay, I hope you can do that. Please try. Example: how many ways can we distribute 6 chocolates of different brand to 4 children without making anyone cry? What I mean is, every child should get at least one chocolate, otherwise they will cry. Okay. Now in this case, each distribution will be like a onto function from set of chocolates to set of children. Okay. So now in the above formula, you take m equal to 6, n equal to 4, then you count onto functions. That will give you number of distributions with required condition. Okay, so then the total number of distribution without making any child cry going to be, in the above formula we are setting n equal to 4, m equal to 6, right? So that will give this expression. This will be simplified to 1560. Therefore 1560 ways we can distribute these 6 chocolates to 4 children without making anyone cry. Okay. Okay, what should be the expansion for x plus y all to the power of 4? We know the meaning of x plus y all to the power of 4, which means x plus y into x plus y into x plus y into x plus y 4 times. If we multiply, we get 2 into 2 into 2 into 2, 2 to the power of 4 terms, right? Because to make a term in each factor, we can use either x or y. So we have two choices. So 2 into 2 into 2 into 2, 2 to the power of 4. Total 16 terms like this we'll get. These are all 4 permutations of x and y you can make. Okay. Now let's classify these 16 into 5 groups. Permutation with 0 y's, permutation with 1 y, permutation with 2 y's, permutation with 3 y's, and permutation with 4 y's, like this. Okay. In this group we have a 0 y's. In this group we have a 1 y. In this group we have a 2 y's. In this group we have a 3 y's. In this group we have a 4 y's. Okay. Now this one I want to realize like this: 4 factorial by 4 factorial 0 factorial. That is nothing but number of permutations you can make using 4 x's alike 0 y's. Okay. Here this 4 I want to realize as 4 factorial by 3 factorial 1 factorial. That is nothing but number of permutations we can make using 3 x's alike 1 y alike. Okay. These 6 terms I want to realize like this: 4 factorial by 2 factorial 2 factorial. Okay, which is nothing but number of permutations we can make using 2x alike 2y's alike. Okay, so these 4 I'm going to realize as 4 factorial by 1 factorial 3 factorial. The number of permutations we can make using 1x alike 3y's alike. So this one I'm going to realize as 4 factorial by 0 factorial 4 factorial. So number of permutations we can make using 0 x's alike 4 y's alike. Okay. So this is nothing but 4 choose 0. This is nothing but 4 choose 1. This is nothing but 4 choose 2. This is nothing but 4 choose 3. This is nothing but 4 choose 4. Okay, so fine. Now each group will simplify to same term here. In the first group we have x to the power of 4 like this. 4 choose 0, x to the power of 4, 4 choose 1, x cube y, 4 choose 2, x square y square, 4 choose 3, x y cube, 4 choose 4, y to the power of 4. Okay, so now you got expansion. So x plus y all to the power of 4 going to be 4 choose 0, x to the power of 4 plus 4 choose 1, x cube y plus 4 choose 2, x square y square plus 4 choose 3 xy cube plus 4 choose 4 y to the power of 4. This should be the expansion for x plus y all to the power of 4. Now we need to generalize it. Okay, what if we take n in place of 4? Okay, we have something called binomial theorem. Okay, next, binomial theorem. Okay, theorem: let x comma y be variables and n be a non-negative integer, then x plus y all to the power of n equal to summation r equal 0 to n choose r times x to the power of n minus r y to the power of r. This is a binomial theorem. Okay. Now let S be the set of all n permutations of xy with repetition. Okay, all n permutations of these two objects x and y with repetition. We know there will be total 2 to the power of n. Okay, now these 2 to the power of n total permutations we are going to classify into n plus 1 groups. Okay, 0 y's group, one wise group, two wise group, and so on, ny. Like, ER be the set of all n permutations of x and y with exactly r wise. Here r equal to 0, 1, 2, so on, n. Okay, total permutations we are classifying into n plus 1 groups. Okay, and each permutation in ER will be associated with a term x to the power of n minus r into y to the power of r, because r wise means n minus r x, right, in permutation. So they get multiplied, will give you x to the power of n minus r into y to the power of r term. Okay, now we know that total S we are classifying into r plus 1 groups, so we must have this. Fine. Next, x plus y all to the power of n means what? X plus y into x plus y into so on n times. Then if you multiply, you get a total permutations, so summation here p varying over permutations, just I'm writing p. Now this all permutations we are now trying to group. So we know that S is what? Union of these ERs for r equal 0 to n. So we are trying to group. Okay, so this is one group. In this group we are grouping all permutation with r wise. Okay, again r vary from 0 to n. Fine. Now we know that each permutation in ER will be associated with a term x to the power of n minus r, y to the power of r. Okay, that's why I'm replacing the permutation corresponding to ER with this one. Okay, now, so here inner summation where p varying over ER. In ER, we know that there are n chooser terms. So we are adding the same thing how many times? Number of elements in ER times, so which is n chooser. So that's why we have binomial theorem. Okay, x plus y equal to the power of n equal to summation r equal to 0 to n chooser x to the power of n minus r, y to the power of r. Next, standard form of binomial theorem. In binomial theorem, if you take x equal to 1, y equal to x, you will get this form. X equal to 1. So 1 plus x. So it will be what? Summation r equal to 0 to n chooser, x is 1. So 1 to the power of n minus r, y is x. So x to the power of r. So that should give this. Okay. This is the standard form of binomial theorem. Now corollary, summation r equal to 0 to n choose r equal to 2 to the power of n. Directly follow from standard form of the binomial theorem. You just plug in x equal to 1. Okay, you will see this identity. Next, summation r equal to 0 to n choose r times minus 1 to the power of r equal to 0. This time you take x equal to minus 1, you will see this identity. Now, summation r equal to 0 to n choose r times 2 to the power of r equal to 3 to the power of n. You take x equal to in the standard form of the binomial theorem, you will see this identity. These are all directly follow from binomial theorem. Okay. Next. Note, n choose r is called binomial coefficient because of the role it played in the binomial theorem. Okay, here both n and r are non-negative integers. Here n I want to call top parameter, or maybe bottom parameter. Both are non-negative. Here n choose r, we already know npr by r factorial, and we know that npr going to be n into n minus 1, n minus 2, so on, n minus r plus 1. So n choose r, you can write n into n minus 1, n minus 2, so on, n minus r plus 1 by r factorial. Okay. Now we are going to generalize this binomial coefficient as something called extended binomial coefficient. Okay. Just looking at this expression, we want to generalize this. Okay. here we generalize n to be real number. Okay, let u be a real number. This is going to be top parameter, and k is a non-negative integer, which is going to be bottom parameter. Then extended binomial coefficient, we denote still the same notation. Still we read it as u choose k, but nothing like choosing k objects from u objects, because u is any real number. It may not make sense. Okay, it is defined, u choose k defined as u into u minus 1, u minus 2, so on, u minus k plus 1 by k factorial when k positive, and 1 when k equal to 0. This is going to be the definition for extended binomial coefficient. Okay, this makes sense when u is any real number, but k must be non-negative integer. Okay, it should be integer and non-negative. Top parameter we are generalizing to be real number, but bottom parameter k still non-negative integer. Okay, now let's see example 1. Find the value of minus 2 choose 3. Here the top parameter is minus 2, so we are trying to find extended binomial coefficient. Okay, with the definition, u choose k equal to u into u minus 1 into u minus 2 up to u minus k plus 1. I can also write u minus of k minus 1 by k factorial. Okay, we go up to k minus 1. So now here u equal to minus 2, k equal to 3. So minus 2 choose 3 going to be minus 2 into minus 2 minus 1 into minus 2 minus 2 by 3 factorial. So which is going to be minus 24 by 6 is going to be minus 4. Okay, this is the minus 2 choose 3 value minus 4. Okay, next find the value of choose 3. Okay, here the top parameter u equal to of and k equal to 3. So now again of choose 3 going to be of into of minus 1 into of minus 2 by 3 factorial. That means of into minus of into minus 3 by 2 by 6 is going to be, so minus into minus plus, so 3 by 8 into 6, this 2 gone, so 1 by 16. Okay, so of choose 3 value 1 by 16. Next, note when the top parameter is negative integer, then this extended binomial coefficient can be expressed in terms of ordinary binomial coefficient. When I say ordinary binomial coefficient, I mean the top parameter is non-negative integer. Okay, that's when I say ordinary binomial coefficient. Okay, that is, if n is a positive integer and u, the top parameter u is minus n. If n is a positive integer, minus n going to be negative integer. So if you take u equal to minus n where n is positive integer, then if you look at extended binomial coefficient minus n choose k, according to the definition, we write u into u minus 1, u minus 2, so on, u minus k plus 1 by k factorial, right? Just replace u with minus n here, it look like this. Now there are k factors. In each factor, if you take minus 1 out, you will get minus 1 to the power of k common. Then you will see this is going to be n, this will become n plus 1, this will become n plus 2, so on. This becomes n plus k minus 1. Denominator as it is k factorial. Next, you just put it in reverse order. First I am writing n plus k minus 1, next I will write n plus k minus 2 so on, the last I will write n. I'm just putting this product in reverse order. Okay, now you multiply and divide by n minus 1 factorial. So here you see n plus k minus 1, n plus k minus 2 up to we have n. Now I multiplied and divided by n minus 1 factorial. What is n minus 1 factorial? N minus 1 into n minus 2 into up to 3 into 2 into 1. If you look at the numerator, n plus k minus 1 into n plus k minus 2 so on up to n into n minus 1, n minus 2 so on 3 into 2 into 1. So this is going to be minus 1 to the power of k n plus k minus 1 factorial by the denominator we have a k factorial and we have a n minus 1 factorial. Okay, so in the next step it's going to be this minus n choose k going to be minus 1 to the power of k into n plus k minus 1 factorial by k factorial n minus 1 factorial. Okay, so now this n plus k minus 1 factorial by k factorial n minus 1 factorial can be realized as n plus k minus 1 choose k. Okay, here this is going to be ordinary binomial coefficient. Ordinary binomial coefficient. Why? Because n is non-negative, k is non-negative. So n plus k minus 1 going to, n is in fact positive, k is non-negative. So n plus k minus 1 going to be non-negative. Minus n is negative. So n is going to be positive. So n plus k minus 1, the top parameter going to be non-negative. That's why it's going to be ordinary binomial coefficient. That's why here the next step we can write minus n choose k as minus 1 to the power of k into n plus k minus 1 choose k. So this is ordinary binomial coefficient. Okay. Okay. Extended binomial theorem. Let x be a real number with mod x less than 1 and u be a real number, then expansion of 1 plus x whole to the power of u going to be summation k equal to 0 to infinity u choose k times x to the power of k. Okay, see here the mod x less than 1 is kind of necessary to guarantee that the right hand side expression is meaningful. As you see, it is an infinite series, right? It may diverges, but it will be guaranteed to converges when mod x less than 1. Okay, so that's why this condition is kind of necessary to make sense out of the right hand side expression. Okay, this is not the problem when we talk about binomial theorem. In binomial theorem, in the expansion we have only finitely many terms, right? So no matter what x you take, the finite sum always makes sense. Okay, so fine. Now proof. The proof is from calculus. Simply, if you take the function f of x equal to 1 plus x whole to the power of u, this will be infinitely many times differentiable. Then you can talk about Taylor series about 0. You can also call it Maclaurin series. If you write Maclaurin series for this function, that will be exactly the right hand side. That's the proof. Okay, we are not going to do it here. You can, it's from calculus. Okay, next, if u equal to minus n, where n is a positive integer, that means if u is negative integer, then extended binomial theorem can be expressed as follows: 1 plus x whole to the power of minus n, where n is positive integer, so minus n going to be negative. Okay, here, okay, fine. Then according to extended binomial theorem, first step I can write summation k equal to 0 to infinity minus n choose k into x to the power of k. That's fine. But when the top parameter is negative integer, this extended binomial coefficient we can express in terms of ordinary binomial coefficient like this. Okay, so this is going to be the expansion for 1 plus x whole to the power of minus n when n is positive integer, so this minus n is going to be negative integer. Okay, fine. If you want expansion for 1 minus x whole to the power of minus n, you simply realize like this: 1 plus minus x whole to the power of minus n. In the above expansion, replace x with a minus x. So then what happened? Summation k equal to 0 to infinity minus 1 to the power of k n plus k minus 1 choose k minus x whole to the power of k. Now what? Here, if you bring this minus outside, it will become minus 1 to the power of k, minus 1 to the power of k, minus 1 to the power of k, minus 1 to the power of 2k, minus 1 to the power of 2k, always positive. So, summation k equal to 0 to infinity n plus k minus 1 choose k x to the power of k. So, this is going to be the expansion for 1 minus x whole to the power of minus n. So this we will be using in coming expansions. Okay, next, some useful expansion of 1 by 1 minus x. 1 by 1 minus x, first we can write 1 minus x whole to the power of minus 1. So here this look like 1 minus x whole to the power of minus n, where n equal to 1. Okay, now how do you write this? Summation k equal to 0 to infinity 1 plus k minus 1 choose k. This 1 cancel. So we have a summation k equal to 0 to infinity k choose k into x to the power of k. This ordinary binomial coefficient. K choose k is 1. So summation k equal to 0 to infinity x to the power of k will give you series 1 plus x square plus x cube and so on. This is something called geometric series. Okay, next. Now expansion for 1 by 1 minus x whole square. This we can write 1 minus x whole to the power of minus 2. This look like again 1 minus x whole to the power of minus n, but where n equal to 2. So how do you write? Summation k equal to 0 to infinity, because 1 minus x whole to the power of minus n expansion is what? Summation k equal to 0 to infinity n plus k minus 1 choose k x to the power of k. Okay, so now n we have to use 2, so this is going to be 2 plus k minus 1 choose k means k plus 1 choose k, but k plus 1 choose k same as k plus 1 choose 1, which is going to be k plus 1. That's why summation k equal 0 to infinity k plus 1 into x to the power of k. So therefore the series is going to be 1 plus 2x plus 3x square plus 4x cube and so on. Okay, next. Then the expansion for 1 by 1 minus x whole cube. Now this we can write 1 minus x whole to the power of minus 3. Again this look like 1 minus x whole to the power of minus n, but n equal to here 3. So now according to this I can write summation k equal 0 to infinity 3 plus k minus 1 choose k times x to the power of k. This you can write k plus 2 choose k same as k plus 2 choose 2, which is going to be k plus 2 into k plus 2 minus 1 by 2. So which is k plus 2 into k plus 1 by 2. Okay, fine. So this will give you 1 plus 3x plus 6x square plus 10x cube and so on. Okay, these are some useful expansion that will come up a lot. Okay, next multinomial theorem. Let x1, x2, so on, xr are real numbers. Then expansion for x1 plus x2 plus so on xr all to the power of n going to be summation. Here the summation varying over all non-negative integer solutions of this equation. The terms are n choose n1 comma n2 comma so on nr into x1 to the power of n1 into x2 to the power of n2 so on xr to the power of nr, where this n choose n1 comma n2 comma so on nr equal to n factorial by n1 factorial n2 factorial so on nr factorial. These are called multinomial coefficients. Okay, this the proof of this one is going to be pretty similar to the proof of the binomial theorem, but just generalization. Instead of using n permutations of two objects x comma y, here you have to think about n permutations of r objects x1, x2, so on xr. Okay, so it will be pretty similar to that proof. Okay, I want you to think about it. Okay, I want you to try. Okay, at least get some intuition why coefficients happen to be these things precisely. I hope you'll understand. Okay, let me do the problems. Example, find the expansion of x plus y plus z all to the power of 4. Okay, so now using multinomial theorem we will expand this. So you think like a x1 plus x2 plus x3 all to the power of 4. Here n equal to 4. Okay, here r equal to 3. Okay, we know that for every non-negative integer solution of this equation there will be one term. Okay, how many non-negative integer solutions of this equation? N plus r minus 1, choose r minus 1, right? So 4 plus 3 minus 1, choose 3 minus 1. Okay, this is going to be 6, choose 2. So there will be 15 terms. Okay, for every non-negative integer solution of this equation there is a corresponding term in the expansion, right? So using multinomial theorem the expansion will be like this. Okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, yeah, total 15 terms. Okay, for every non-negative integer solution of this equation there is a corresponding term here. Okay, for example 1 comma 1 comma 2 is one solution of this equation, so the corresponding term going to be 4, choose 1 comma 1 comma 2 x to the power of 1 y to the power of 1 z square, like this. Okay, so then after simplification the expansion will be like this. Okay, so this is going to be expansion for x plus y plus z all to the power of 4 using multinomial theorem. Thank you. Okay.